Picture a sawmill in Oregon, 1908. The morning shift has just started. The smell of fresh-cut pine fills the air. In the center of the mill floor stands a circular saw blade, 10 feet in diameter, 120 teeth. Each tooth 6 inches long, sharpened to a point. The blade spins at 1,000 revolutions per minute. A worker named Jacob Lindstrom feeds a Douglas fir log into the blade. The log is 8 feet long, 2 feet thick. The blade cuts smoothly for the first 6 feet. Then the blade hits a knot. The wood grain twists. The blade binds. For a fraction of a second, the blade slows. Then the motor catches up. The blade accelerates. The log does not continue through. It reverses. The log flies backward at 90 miles per hour. Jacob is standing 4 feet behind the blade. The log strikes him in the chest. His ribs collapse. His heart stops. He is dead before he hits the floor. This is not a story about one saw. This is a story about the machine that turned lumber into projectiles. The blade that spun too fast to see and too powerful to stop. The equipment that killed more sawmill workers than any other piece of machinery in the timber industry. Before modern bandsaw mills and computer-controlled cutting, processing logs into lumber required massive circular saw blades. These were not the handheld saws familiar to homeowners. These were industrial monsters. The smallest commercial sawmill blades measured 6 feet in diameter. The largest measured 14 feet. A 10-foot blade was standard for mills processing old-growth timber. The blade itself weighed between 800 and 1,500 pounds. A solid steel disc with teeth cut into the rim. Each tooth was individually sharpened and set at precise angles. The blade was mounted on a horizontal shaft, driven by a steam engine or an electric motor producing 50 to 200 horsepower. When the blade reached operating speed, the rim moved at 150 miles per hour. The teeth became invisible. The blade became a screaming disc of metal that could cut through a 2-foot-thick log in 30 seconds. The physics of the circular saw made it fundamentally dangerous in ways that other cutting tools were not. A bandsaw blade moved in one direction on a continuous loop. If the blade encountered resistance, the motor would stall or the blade would break, but the wood stayed relatively stationary. A circular saw blade rotated on a fixed axis. When the blade encountered resistance, rotational momentum kept the blade spinning. The blade did not stop. It grabbed. The cutting action of a circular saw was not a clean slice. It was a series of thousands of impacts per minute. Each tooth hit the wood, removed a chip, and moved on. The next tooth hit and removed another chip. 1,000 revolutions per minute meant the blade completed 16 complete rotations every second. A 10-foot blade with 120 teeth presented 2,000 cutting edges to the wood every second. This was not cutting. This was controlled demolition. The danger began with kickback. When a circular saw blade bound in the wood, rotational physics took over. The blade grabbed the wood and tried to continue rotating. If the wood was held firmly by the feed mechanism, the blade would stall. If the wood was not held firmly, the blade would throw it. The direction of the throw was always the same, backward, toward the operator. The speed of the throw depended on blade speed and the mass of the wood. A small board might fly backward at 50 miles per hour. A large timber might fly backward at 90 miles per hour. The wood became a battering ram. Workers standing behind the blade had no chance to react. The time between the blade binding and the wood flying backward was less than 1/10 of a second. Human reaction time is approximately half a second. By the time a worker recognized danger, the timber had already struck them. The impact broke ribs, crushed sternums, and caused massive internal injuries. Workers did not die from being cut. They died from being hit by lumber moving at highway speeds. Blade binding occurred for multiple reasons. The most common was hitting knots in the wood. A knot is where a branch grew from the trunk, and the wood grain twists around it. The grain density increases. When the saw blade hit a knot, The cutting resistance rose dramatically. The blade slowed slightly, and the motor supplied more power. The blade sped back up, but in that fraction of a second when the blade was slow, the teeth grabbed the wood differently. Instead of cutting cleanly, the teeth hooked into the grain, and the blade pulled the wood. If the wood was not secured, it moved. Once wood started moving against the direction of the blade rotation, kickback was inevitable. The blade grabbed harder, it accelerated the wood backward, and it launched the piece toward the operator. The second cause of kickback was improper wood placement. Logs were not uniform. They had bark, irregular surfaces, and internal stresses from growing on slopes or in wind. When a log was fed into the blade at a slight angle, one side contacted the teeth before the other. The blade would grab the side that made contact first, and that would twist the log. A twisting log in a circular saw was deadly. In 1912, a sawmill in Washington state had a log twist during cutting. The blade threw the log sideways. The log struck two workers standing 15 feet away. Both died. One was hit in the head, the other was hit in the abdomen. The log weighed 300 pounds and was moving at approximately 70 miles per hour. The impact was equivalent to being hit by a small automobile. The third cause of kickback was blade maintenance failure. Saw teeth dulled with use. A dull tooth did not cut, it pushed. When enough teeth became dull, the blade would push the wood instead of cutting it. The wood would resist, the blade would bind, and kickback would follow. Sawmill operators were supposed to sharpen blades daily, but many did not. Sharpening took time, and time was money. Mills often ran blades until they were obviously dull, and then they sharpened them. By that point, dozens of workers had been exposed to increased kickback risk for days or weeks. Some mills tried to extend blade life by increasing motor power instead of sharpening teeth. That made kickback worse. More power meant the dull blade grabbed harder when it bound, and the wood flew backward faster. The size of industrial saw blades made them uniquely dangerous in another way. The blade extended several feet above the cutting table, so workers could not see over it. They could not see what was happening on the other side. If a log twisted or bound, the operator on the feed side would not know until the log came flying back. Some mills installed mirrors above the blade so operators could see the backside. That failed because sawdust covered the mirrors within minutes. The operators could not see. They cut blind. They fed logs into a 10-foot disc of spinning steel and hoped the wood came out the other side instead of flying backward into their chest. Blade failures were the other major killer. A circular saw blade spinning at 1,000 revolutions per minute stored enormous kinetic energy. If the blade cracked or a tooth broke off, that energy released catastrophically. A broken tooth became a projectile. 6 inches of sharpened steel, moving at 150 miles per hour, could fly as a deadly missile. The tooth would fly in whatever direction it was traveling when it separated from the blade. Sometimes it hit the floor or the ceiling. Sometimes it hit a worker. In 1906, a sawtooth broke off in a Michigan sawmill and struck a worker in the throat. The tooth severed his carotid artery. He bled out in less than 2 minutes. The tooth had traveled 60 feet from the blade before hitting him. There was no protection. There was no warning. The blade simply disintegrated and killed someone. Complete blade failures were worse. A crack could propagate across the entire blade. The blade would shatter into multiple pieces. Each piece would fly outward from the center. The pieces were large, sharp, and moving at tremendous speed. In 1914, a blade shattered in a California sawmill. 3 workers were killed. One was struck in the head by a piece weighing 40 pounds. Another was struck in the chest by a piece weighing 30 pounds. The third was struck in the legs by multiple smaller pieces and bled to death from severed arteries. The blade had shown no signs of cracking before failure. It had been inspected the previous week and judged safe. The metal simply fatigued from millions of rotations and failed without warning. The sound of a sawmill made blade failures more dangerous. The noise level in an operating mill was extreme. The saw blade screamed. The motor roared, steam engines hissed, lumber crashed onto tables. Workers could not hear warnings. They could not hear the change in blade sound that might indicate a developing crack. They worked in constant, deafening noise and trusted that the blade would hold together. When the blade failed, they did not hear it coming. They only felt the impact when a piece of blade struck them. Some workers survived blade impacts and described the experience. They said it felt like being hit by a vehicle. Sudden, overwhelming force. Then pain, then nothing. Sawmill owners knew circular saws were killing workers. Accident reports were filed with state labor departments. Insurance companies tracked sawmill deaths separately from other industrial accidents because the rates were so high. In 1910, the Washington State Department of Labor reviewed sawmill fatalities over a 5-year period. They found that circular saws were responsible for 42% of all sawmill deaths. This was higher than log handling, higher than machinery maintenance, higher than any other single cause. The circular saw was the most deadly piece of equipment in the most dangerous industry in America. The department recommended mandatory blade guards, anti-kickback devices, and reduced blade speeds. The recommendations were not enforced. Mill owners argued that guards would reduce productivity and that anti-kickback devices were unreliable. The economic calculation was familiar. Installing safety equipment cost money. A blade guard for a 10-foot saw cost approximately $200. Anti-kickback devices cost another $300. Reducing blade speed meant slower cutting and reduced output. A mill could process perhaps 20% less lumber per day at safer speeds. Mill owners calculated that it was cheaper to pay wrongful death settlements and hire replacement workers than to install safety equipment and reduce production. In 1912, the average wrongful death settlement in Washington state was $500. A mill could kill 2 workers per year and still save money by not installing safety equipment. The math was brutal and clear. Safety cost more than death. Workers developed informal survival strategies. Experienced sawyers learned to read wood grain and identify knots before the blade reached them. They would slow the feed rate when approaching a knot to reduce kickback risk. This worked only if they could see the knot. Bark-covered logs hid knots. The sawyer would not know the knot was there until the blade hit it. Other workers positioned themselves to the side of the blade rather than directly behind it. This reduced the chance of being hit by kickback, but increased the chance of being hit by a flying sawtooth if the blade failed. There was no safe position. Standing behind the blade meant kickback risk. Standing beside the blade meant blade failure risk. Standing anywhere in the mill meant risk from someone else's saw-throwing wood or teeth. Some mills tried installing physical barriers behind the saw blade to stop kicked-back lumber. Heavy wooden walls or steel plates positioned 6 feet behind the blade. This failed because the barriers had to have gaps for the operators to stand in. The kicked-back lumber simply flew through the gaps and hit the operators anyway. The barriers also could not stop saw teeth. A 6-inch steel tooth moving at 150 miles per hour would penetrate a 2-inch wooden wall. The barriers provided an illusion of safety, but no actual protection. The blade speed was determined by production requirements, not safety considerations. Faster blades cut faster. Faster cutting meant more lumber per day. More lumber meant more profit. Mills ran their blades as fast as the motors could turn them. Some mills modified their motors to increase blade speed beyond manufacturer specifications. This increased both productivity and danger. The faster the blade spun, the faster kicked-back lumber flew, and the more energy was stored in the blade for catastrophic failure. Workers had no control over blade speed. The mill foreman set the speed based on production quotas. The workers simply operated the equipment they were given and hoped the blade stayed intact and the wood fed smoothly. Children worked in sawmills, not operating the saws but removing cut lumber from the outfeed tables and stacking it. These children, some as young as 12, worked within 20 feet of the spinning blade all day. They were killed by kicked-back lumber and flying saw teeth at rates comparable to adult workers. In 1909, a 14-year-old boy was killed in an Idaho sawmill when a kickback plank struck him in the head. He had been stacking lumber. He was not even involved in the cutting operation. The lumber flew off the saw, over the outfeed table, and struck him 20 feet from the blade. The mill was not fined. Child labor in sawmills was legal. The death was recorded as an industrial accident. His family received no compensation because he was not the primary wage earner. The sawmill industry did not improve safety until forced by regulation and technology. In the 1920s, several states began requiring blade guards and anti-kickback devices on new sawmill installations. Existing mills were grandfathered in and not required to retrofit. The old dangerous saws kept running for decades. Technology eventually made circular saws less dominant. Bandsaw mills became practical in the 1930s. A bandsaw blade was a thin loop of steel with teeth on one edge. Bandsaws cut faster, wasted less wood, and were significantly safer. Kickback was nearly impossible because the blade moved in one continuous direction. Blade failures were less catastrophic because the blade was thinner and stored less energy. By 1950, most large sawmills had converted to bandsaws. The great circular saws were scrapped or sold to smaller operations. The workers who had spent decades feeding logs into 10-foot spinning discs simply moved to the new equipment. The sawmills found new ways to injure people, but nothing matched the circular saw for consistent lethality. The total death toll from circular saws in American sawmills is difficult to calculate precisely. Many mills did not keep detailed records. Many deaths were attributed to other causes. A worker killed by kickback lumber might be listed as dying from blunt force trauma rather than saw kickback. A worker killed by a blade fragment might be listed as dying from penetrating injury rather than blade failure. But estimates from timber industry historians suggest that between 1880 and 1940, circular saws killed at least 3,000 workers in American sawmills. That is one death every week for 60 years. This does not include non-fatal injuries. This does not include workers who lost hands or arms to the blade itself rather than being killed by kickback or blade failure. These are deaths only. Most were men between 20 and 40 years old. Most left families with no compensation. Most were forgotten within months. For 60 years, circular saws were the standard in lumber production. 10-foot spinning steel, 1,000 revolutions per minute, 120 teeth moving too fast to see. The blade cut through logs in seconds. When the blade bound, the log flew backward, faster than a worker could react. When the blade failed, the fragments flew outward, like shrapnel from an explosion. You fed logs into the blade all day. You stood behind it or beside it because there was nowhere else to stand. You listened to the scream of a metal cutting wood and hoped the next log would feed smoothly. You hoped the blade would hold together. You hoped that when kickback happened, and it always happened eventually, you would not be standing in the path. Sometimes you were lucky. Sometimes the lumber flew past you, or the blade tooth missed you. Sometimes you were not lucky. The blade grabbed the wood wrong. The timber flew backward. You had 1/10 of a second to react. Human reaction time is half a second. The math was simple and fatal. The lumber struck you at 90 miles per hour. The impact broke bones and ruptured organs. The blade kept spinning. The mill kept running. Someone else took your place at the saw. The blade did not care. The blade just spun faster than sight, more powerful than caution, turning lumber into boards and workers into casualties. Before bandsaw mills revolutionized timber processing, cutting logs into lumber required massive circular saw blades that could measure up to 14 feet in diameter and spin at speeds exceeding 1,000 revolutions per minute. At the height of American timber production, these blades turned at speeds that made their teeth invisible, cutting through old-growth logs in seconds, while storing enormous kinetic energy. When the cutting was smooth, sawmills processed thousands of board feet each day. When blades hit knots in the wood grain or encountered internal stresses, rotational physics transformed lumber into projectiles. Logs weighing hundreds of pounds flew backward at 90 miles per hour, in less than a tenth of a second. Workers standing behind the blade had no time to react. This documentary examines how circular saws became essential to lumber production, the physics that made kickback inevitable rather than preventable, why blade failures turned 6-inch steel teeth into shrapnel, and the economic calculation that faster blade speeds meant higher profits regardless of casualty rates. It is a story of rotational momentum, human reaction time, and the difference between cutting wood and launching it as a weapon.